Hello, everyone. Thank you for coming to the MTV Nuclear Engineering Summer School. Today, we'll be hearing about pulse processing and characterization of organic scintillators from Ethan Schneider. He is a PhD candidate in Professor Potsy's Detectors for Nuclear Nonproliferation group, just like just like myself. Courtney Wagoner, program our program coordinator, has just issued an important reminder in the chat to use the Q&A for specific questions related to the lectures. If you have logistical questions, you can DM Courtney or myself. I'll be monitoring questions in chat as we go on. Do not use the raise hand feature because we will get to all questions for the presenter at the end. Thanks, everyone. And Ethan, let's take it away.
All right, thank you, Erin, for that introduction. As mentioned, I'll be discussing pulse processing and scintillator characterization. This will be like a broad overview talk about all these different characterization methods that we will use, that we ourselves use in the lab, as well as some other characterization methods that are done elsewhere. So I want to, as a broad focus, what might be the importance of doing this, looking at these detectors and characterizing them. So as you might know from the number of talks that were given at the summer school, radiation detection has many different applications. We have, of course, due to these various applications, we have different items that we want to account for. Specific radiation detectors there's not one perfect detector, so we have to kind of look at the application we have and identify detectors that fit this application the best. And so there are a number of different parameters we can optimize for here. So one that's we don't really have to look at in the laboratory is, of course, cost. Different detectors cost different amounts of money for different sizes. So earlier this week, in like organic glass, that's a little bit of a costly material in comparison to something such as a plastic or a liquid scintillator in terms of volume, active volume. Another thing to consider is that while organic glass is more expensive than some plastics, you might also have different properties of this, such as energy resolution and timing resolution, which are important for your application that you need to have a certain threshold or different resolution for your application. For instance, this is very important for like a Ricardo's dual particle imager that was talked about last week, where you want something with great timing resolution as well as sensitivity to both neutrons and photons, and the ability to distinguish between the two. So there's that added component of what else you might need there. Another component of this might be durability. So for a large array that's not moved around, such as the chi-nu array pictured here, which is used for physics experiments, you don't really have to have a very durable system here because you're not moving it, as opposed to something that's going to be used on the field, such as this imager here on the bottom, as well as this inspector on the right. This one on the right is made with a sodium iodine detector, which is pretty rugged, but it is sensitive to water, so you have to be considerate about that. Another item is, of course, weight. How much material do you want? How heavy it is, and this is not just the weight of the detector itself, but all the electronics that come with it, such as are you going to be what kind of light readout you're going to be working off of. So, and just to give a wide view again of what we're looking at whenever you have a radiation detection system, we will have some kind of detector, in this case a scintillator, which radiation will come in and produce light. This light is then scattered into our light readout system, whether it be a PMT, photomultiplier tube, or a silicon photomultiplier. From that, so we have radiation converted into light, light converted into electrical pulse. And this pulse we read out with a digitizer to record this information. So this first light readout that has been talked about a few times within the summer school is the PMT. So this PMT works by it's a vacuum tube in which we have a series of different diodes which will multiply an electric signal in the system. So on the far left, you have our scintillator, which is wrapped with some kind of reflector to get more of that light into our light readout. Here we have the photoelectric effect, which converts this light into electrons. And these electrons are then multiplied, so we go from a tiny signal which we cannot read into something we can actually read out with our system. I also want to point out that you're going to have some kind of coupling compound within the system. So you have some kind of optical grease. So it's not just a scintillator laying on your PMT, but there's something there to make sure you have complete attachment. Another item here is that we have the photomultiplier, the silicon photomultiplier, which is a very different system as it uses um, semiconductors. It's a pixelated detector, which is an avalanche detector with a set operating voltage. The operating voltage of these PMs are significantly smaller than that of the PMTs, and they're also much smaller detectors. That's something you might want to think about. With a PMT, the smallest one we have in our lab personally is around 1.5 inches in, it has a 1.5 inch radius. So you can, as opposed to this IPM, which is on the order of like 20 or so millimeters, I believe. So you're able to have a much more dense system here in comparison to those photomultiplier tubes if you want to have many detectors close to each other, as seen by that dual particle imager. And it's also a lot more compact. So you can have all these channels onto a single board. So that there's a lot of advantages there. One disadvantage you might know is that the gain of this IPM is not independent on temperature. So long as this shouldn't be an issue, so long as you're working with your detector in a area where the temperature is constant, such as your laboratory. However, if you're out in the field where you're going from 70 degrees, 60 degrees, 90 degrees, you'll have to have some kind of you'll have to account for this or have some kind of cooling system for this. So now that we have our scintillator, which produces light, and this light is produced into a signal, we now need some kind of equipment to process this information. This is done through a digitizer, which will convert this analog pulse in our cables into information. The digitizer has a number of uses within here, where it does baseline calculation. So uh, whenever you have your pulse, you have a constant background. It'll have an idea of what the actual baseline of your voltage is. From there, in addition to this, it does your waveform collection. So as it actually gets a pulse, it will now record the shape of that pulse, its different amplitude as a function of time. And the length of the pulse is something you set yourself. So you need some kind of information beforehand of how long my pulse is going to be. For the organics, Stobine, organic glass, it's a very short waveform. So you can get away with uh, a waveform time of around 100 to 200 or so nanoseconds. And for something such as a sodium iodide, you're going to have a much longer waveform on the order of microseconds. Another thing that this digitizer does, it handles timing. So this is very important to understand when your pulses are in your measurement. So it's not just about collecting these time tags, but you're also able to do coincidence logic on this. So you might notice that digitizers like these have multiple different channels for you to plug in different detectors. This one has 8 channels here, and it's a 14-bit digitizer. What this means is you can have multiple detectors plugged in at once, and you can reject some pulses based on coincidence logic. Meaning, so as if I have a pulse in channel 0 and a pulse in channel 2, I'll record those pulses so long as they're within 200 nanoseconds of each other. Then this will come into play a little later in the presentation. Another thing you have to consider when working with these for this characterization experiments is you need to account for your data throughput. These digitizers will have a maximum data throughput, which will be dependent upon your count rate as well as how long your pulses are. And if you have too many counts per second and too many channels, you can overwhelm your digitizer and you'll start losing pulses. So as I mentioned earlier, we have determination of that time tag is quite important. And the way this is done is we have 2 different options available to us. For one, we have leading edge discrimination, which is something it's pretty intuitive, where you have that baseline and you just have a set trigger level. So this is given by some kind of voltage, and whenever it passes above this voltage, we collect that time it passes over, and that's our time tag. But if you think about this, since we have a pulse that's going to have some kind of noise to it, some electronic noise of jitter, we're not going to have a smooth function. And therefore, we're going to have this variance within this trigger level just due to noise. It might jump above, it might jump below. So there's going to be some variation, some uncertainty in that leading edge, unfortunately. That's what we refer to as time jitter. Another component is, of course, amplitude walk. So within our detector, we're producing all these pulses. And these pulses will have different amplitudes based upon the number of the energy of the particle which we're capturing, right? So this larger pulse could correspond to 2 MeV, the lower pulse could correspond to 1 MeV. Note that the amount, the amplitude of this pulse will then impact where on this leading edge our trigger level is triggered. We refer to this as amplitude walk. Notice how at the on the upper half of this pulse, we have that trigger, and on the lower half of this pulse, we have this trigger. So in a situation where we have a large variation in energies that we're going to be detecting, it might not be prudent to use a leading edge discrimination. So we can use, in order to circumvent this, we can use constant fraction discrimination, which is a process in which we take our pulse, and we just split it in half, so we have two identical pulses, and then we attenuate by some kind of fraction, hence constant fraction, delay it, invert it, and add it together. And this process goes from a single lobe pulse into something that has the two lobes, both a negative region and an upper positive region, and we take that zero crossing time as our time tag, and this is less susceptible to the amplitude walk as mentioned in the previous slide. So now that we have our detector, now that we have our digitizer light readout, we're able to collect we're able to collect our waveforms of our detectors. To the left are a series of waveforms collected for the gammas as well as neutrons of a constant amplitude. So over time, as we collect all these different waveforms, we are able to create a histogram based upon either their total integral or just an amplitude. And you can see that on the right, where you just have these two different distributions, where you have an organic pulse height distribution on the right, where you do not have that photo peak, but we have this constant edge. And this is just a histogram based upon all these counts here. You have to keep in mind that whenever working with a pulse integral and pulse amplitude, we will get a very similar result, but they'll just have a different scaling factor. In order to account for the scaling, we have to do an energy calibration. So our constant edge will give us an idea of what an energy that corresponds. What voltage, so what amplitude, pulse amplitude, or what pulse integral correspond to a specific energy. So within our laboratories, we'll have different check energy sources. So for instance, we'll have a 662 cesium spectrum. We might have cobalt. We might also have sodium 22, which will give us those 511 kV and 1278 kV energies to work off of. And from this, we'll be able to fit a Gaussian distribution to these edges of our Compton edges to get these values based upon the Compton scatter equation. We'll know what energies correspond to these Compton edges and do our energy calibration to these. So from this, we have a linear response between our different scintillators, and we're able to go from this lab value of pulse amplitude, pulse integral into an energy value. So now that we have an energy resolution, now that we have a calibrated detector, we're able to start doing things such as calculating the energy resolution of our detector. So energy resolution gives us an idea of how well we can the smear that we'll get from a single energy source. So in an ideal world with perfect energy resolution, we expect for a monoenergetic source, we'd expect just a single peak, a single line of a negligible width. Due to energy resolution, we'll get some broadening of this, and it goes from a peak into a Gaussian distribution. This will also greatly impact what our distributions actually look like, as you can see on the right. Here we have a photo absorption peak on this far right for a 662 kV cesium source, where you have full absorption of this for a photoelectric absorption. On the left, you have the constant edge associated with this, with these different energies from constant scatters. We also have can also have backscatter peaks. We do not have a annihilation peak within this measurement because it doesn't have high enough energy. You can see some X-ray peaks at the very bottom. So this energy resolution will vary greatly by our detector that we're using. Organics themselves have around 10% energy resolution, as opposed to sodium iodine, which has a greater energy resolution, and significantly greater resolution is through high purity germanium detectors, which are less than 1%. So this energy resolution value is calculated by looking at on the left, we have like a photo peak, and we're able to take the width of this peak and just divide it by its energy to give us this energy resolution. And note that energy resolution is dependent upon the energy of the source itself. And this resolution will increase as we increase in energy. And this is primarily just due to as we increase our energy, we're getting more charged particles or more information carriers. So we should increase this. This will increase our resolution. So as I mentioned before, these organic detectors don't have a photopeak. Well, they do have some photoelectric effects, but since they have low Z material, these are very, very unlikely, and our spectrum is dominated by this Compton edge. On the figure on the left, you can see this Compton edge here, and it has a Compton edge itself is around 478. So we could fit a Gaussian to this to try to get this value, but ideally we do something called an absolute energy resolution measurement. And this is done with a coincidence, done in coincidence with two detectors. The way this measurement would work is that we have some kind of source on the left here. It's producing gammas in all different directions isotropically. And we have our detector of interest. For instance, this is an organic class detector. At some distance, at a certain distance far away, we have another detector, our trigger detector, at a certain angle. And here, we just have these detectors are in coincidence with each other, so we're only recording events in the organic class detector in which gammas will scatter from this detector into this detector. From there, we now have only events that scatter at this angle. And if you can recall from the Compton scattering equation, these gammas will have a certain energy so long as it's a single scatter event. So as they scatter from here to here, all the energies that are deposited in this OGS detector are going to be monoenergetic. And so we should just get this peak here, as well as a few peak counts in the lower energy regions, which are due to triggering on background events. And from here, we're able to measure this full width half max, and therefore we're able to get our energy resolution of the system. In a similar process, we have our timing resolution. So timing resolution has a similar process where we have two detectors in coincidence with each other with a source in the very middle of our system. The source used for this system is a sodium-22. And the important part here is to have an event which is simultaneous, which will give us a signal that's simultaneous with each other. So you could put a cesium-137 source there and it wouldn't work. And the reason that's the case is because cesium-137 source will just be emitting single gammas. Well, sodium-22 will emit a positron. The positron will, and from this positron, we'll get these two 511 gammas, which are emitted in opposite directions, the same energy at the same time. So as long as our detectors are equidistant from each other, whenever an event hits one and an event hits the other, it should be at the same time. And if we were, for instance, if we were to have a perfect detector with 0 timing resolution, we expect to see a single bin here at the very center at 0, 0, where every bin corresponds to that event. However, we do see this spread here as there's some variation in when these events are actually recorded in each detector. So there's that time resolution there. You can see this difference between organic glass as well as our still vein, which are on the order of 350 picoseconds, around 540 picoseconds. Note that these two different detectors have very quite good timing resolution in comparison to other detectors such as sodium iodine. So this kind of brings us back to that first slide where we talked about the trade-offs. So while sodium iodine is significantly cheaper than organic glass and organic glass and stillbean, for this particular use case, we would prefer using an organic scintillator. Another Another component to keep track of is, of course, intrinsic efficiency, and this is a measure of how likely our radiation is to actually interact and produce signals within our detectors. So you can imagine this is very important for whenever looking for sources. And if, for instance, if we have some kind of portal monitor situation where you have detectors on either side looking for materials being moved across a border, radioactive sources, we want to be very sensitive to going to be we want to be very careful that we're actually when radiation passes through a detector that radiation is captured and gives us a signal that we can say, hey, there's a source here. Note that this is very dependent upon our material itself. And the way we define this value is our source strength is our number of counts in our detectors given by our source strength by times intrinsic efficiency times our gamma efficiency. So and here on the right, you can see that breakdown of the different effects that we'll see within our detector based upon our photoelectric effect. Sorry, it's given by our interactions are dependent upon energy and our material type, or just atomic weight in Z. Another component of that equation that was given was detection of our solid angle efficiency or our geometric efficiency. This is just defined by the surface area of the projection of our surface of interest onto a unit sphere. So you can kind of think of it by the area or like the shadow that our detector gives whenever we put a light source nearby. What's that area that shadow or how many photons produced by our isotropic source will actually pass through a detector. So you can imagine this is very dependent upon our source definition and detector geometry. And in most cases, in many of our common cases, there's an analytical solution to this equation here, this surface integral. So a very common one would be this one on the bottom right for a point source with a disk aperture, where this is a pretty easy equation to solve. However, whenever we get a more complex system, the solutions for this analytical function can be very difficult, or in some cases, like impossible. For instance, we have this disk source with a disk aperture, so just the difference between that point source approximation and disk source approximation gives us a much more complex equation to solve for. And this just gives us that ratio of counts that pass through a detector to counts that don't pass through a detector. Or it can also be represented in terms of steradians as opposed to a percentage. So in cases where that method, we have a very complex system where we can't analytically solve for the solid angle, we can use a different approach for this. So one of the best approaches for this is just using the Monte Carlo method. Can be done with our various tools that we have on hand. You might use like a Geont 4, Fluka. You have all these radiation transport codes. We're able to build a geometry within this code and work off of that. And the way it's a pretty simple system, so long as you have your source definition can produce your radiation in different directions. You have your detector, and all these codes will allow you to record the ratio of the ones that pass through your detector and the ones that do not. So this ratio will give you that solid angle. I just want to point out, so whichever method works, you can do either. It's just a trade-off of which will be faster in terms of your workflow. If you have a very simple geometry where it's very easy to define your things, or you're able to make reasonable assumptions to reduce the complexity of it, you might want to opt for this solving calculation. But if you have a very large detector system, or you have many detectors in your system, you're concerned about different, it's not something you can just calculate by hand, and you already have a Monte Carlo, some kind of model for your system, you just ought to use this system. Sorry, I was taking some water. As I mentioned before, we have different abilities within our detectors. One such ability is pulse shape discrimination. So pulse shape discrimination is a way where we're able to distinguish between photons and neutrons within our detector based upon the pulse it produces. So our neutrons and our photons will have a different uh, our neutrons will have a much have delayed fluorescence, will produce this longer tail as opposed to our photons. So by doing a pulsate discrimination, we're just looking at the ratio between the total integral of our pulse, defined by before the pulse to some set time, which is arbitrary, and compare that to a second integral, which is defined by some time after our pulse maximum to the same pulse end time. And whenever we do PSD, we do this for every single one of our pulses, where we take these two integrals and we're able to get a ratio of the two, QS over Q, for every single one of our pulses. And from this, we're able to create a pulse, our heat map based upon this ratio value and the energies of these pulses. You can see an example of one of these heat maps on the left, where you have that neutron lobe on the top, as well as our gamma lobe on the bottom. I want to point out a few different things on this distribution here, is that for one, this is with the Californium source, and we have all these, this is for our Californium source, so we have a continuous spectrum of gamma energies and neutron energies. We can separate into these two lobes. And note that at lower and lower energies, it becomes nearly impossible to be able to distinguish between our neutron lobe and our gamma node. And what we do here is that we apply some kind of line to discrimination. In some cases, it'll be a straight line. In other cases, it'll be a power law fitted to the edge of this gamma edge. And from that, we're able to distinguish between our neutrons and our gammas. And we're able to quantify the ability for us to quantify this peak separation by this figure of merit below. And this figure of merit is just a metric in which we're able to describe how well these peaks are separated. So it's given by our peak separation divided by the widths of these two peaks, the full width half max. So you can take a full width half max of a Gaussian fitted to this bottom lobe to a top lobe for a certain slice, and I'll give you a figure of merit for that. And as you can see, as we go increase in energy, our ability to distinguish between these two lobes increases. This can be seen with this PSD figure of merit plot here, where we see this increase in figure of merit as we increase in energy. This figure of merit is also will also change based upon the tail length that we select. So as I mentioned a couple slides ago, sorry, I could stop this. Sorry. Our PSD figure of merit is also determined by our actually specific tail length that we use. So as I mentioned before, the ratio these integrals are defined by the total integral as well as second integral from a certain value past our pulse amplitude. So here we have our different tail lengths, which will impact our PSD plot. So as you go from around 8 to 12 to 13, and so on, we see better separation, greater separation. At some point, we have an optimized figure of merit value. As I talked about before, our figure of merit is done with this fitting these Gaussians to for a specific slice where we have our gamma peak as well as our neutron peak. We have two fitted Gaussian to these. And from these peaks, we get our full width half max for both our gamma as well as our neutrons, and we get that separation. So as for another component of this is very important to work off of is our looking at our neutron light output. So as been discussed in this lecture and previous lectures, the light produced by gamma pulses are going to be linear with energy. So 1 MeV gamma will have half the light output of one of a great 2 MeV. This is not quite the same for neutrons, as we increase in neutron energy, we do not have a linear relationship. This can be seen on the right, where we have the variation in our proton, our recoil proton energy. So the energy of that proton that moves about in the scintillator following a neutron scatters off protons. Proton recoils. This produces light. And there's some quenching there, which gives us a relationship that's not quite linear. We have various empirical functions that we fit to this light output versus proton recoil curve. And one that's pretty popular is the Burke's function, which is given the bottom left here. So this value here is very important whenever we try to do any kind of detector modeling, as if we do not have proper Burke's parameters or have an idea of how the light output curve looks, if we try to model our detector response, we can do it just fine for gammas because it has a linear response. But if we do not have this for neutrons, we're going to get incorrect results whenever we do this detector modeling. So one thing you might notice on this plot here is that we have a series of these energies here. And so one thing one might try to characterize this by running multiple different monoenergetic sources and looking at the light output at these sources and then working from there. The issue is that we don't, in our lab spaces, the neutron sources that are available to us vary greatly, and they're all, except for like a DT generator, are not monoenergetic. So the spectra on the left is our neutron energy spectra for a QB source given from null, and the right is a same for our is a Californium neutron energy spectra. So as you might expect, as you can see, they are not monoenergetic. So one difficulty here is you want to construct a measurement so that you have monoenergetic neutron sources, or you're able to identify single energies of neutrons and look at what the light output looks for a single energy source. So how can we do that? One of the ways that we do that within a lab is through a time of flight measurement. This is one of those coincidence measurements that was mentioned earlier. So this is a difference. It's a similar setup from that timing resolution measurement, where you have our two detectors. And you have a neutron emitting source on the left, normally californium. And here we have this time of flight where you have a photon, or photons and neutrons are produced by Californium spontaneous fission. Only 3% of them, only 3% of its decays are like this. The rest of them are alphas. And whatever produces this photons and neutrons, we have them recorded in our different detectors. So in a case where we have a trigger in our trigger detector, we get a time 0, and we get our final time in the second detector with our neutron event. And the length of time it gets there gets logged in this time of flight spectra. You can see a few different components of the spectra. We have this gamma neutron event, or it could be a neutron event. We have a trigger followed by a neutron slowly moving on the order of nanoseconds from one detector, from the source to the other detector. In another case, we have a much faster event where you have a photon and a photon event, where the difference between these two events is practically indistinguishable, just because our flight path would be around 1 meter, and speed of light is way greater than that actual path length. So we get something on the order of 0 nanoseconds. We have this width to do that timing resolution. So here we have our, let's look at an example of these different measurements that we could have. So for instance, we have this first neutron that comes fast here. We have that difference in time value around 8 or so nanoseconds. And a slower neutron takes longer time, so we get more counts here, and slower still at around 30 nanoseconds, and even longer at around 40 nanoseconds or even 50 nanoseconds. So here you can look at this lobe structure here, and you can see that based upon the length, this path length that we have, let's say we have 1 meter, we're able to calculate how the energy of our neutron based upon, since we know the distance between the two detectors, and we know the time it takes for our neutron to go this path length. Since we know the neutron mass, we can calculate the energy of the neutron for the single time bin. We can do for another time bin, another time bin, and now we have data which we can confidently say to a certain, we can say to some degree is a single energy of neutrons. And so long as we have enough statistics in each of these bins, we will have monoenergetic or pseudo-monoenergetic neutron sources for a variety of energies, which we can start working our Berks off of. So our distributions that we expect to see is this square distribution based upon our neutron recoil energy. So we have maximum energy deposition and we have a variation just due to different scatters neutrons can take within our system. So for a single scatter, we get with single scatter of a perfect detector with no resolution, we expect to see this distribution here. And whenever we look at a single time slice, we get a similar distribution that's going to be more sloped. And the reason we're going to get more of this sloped shape here is because it's not going to be quite monoenergetic. So this one on the right here is an energy range of 4.03 to 4.27 MeV. So that's an energy range which of around over 200 keV. So you're not going to have that clean edge, and you also have energy resolution here. So one thing you have to consider whenever you're working with this kind of experiment like this is how long we have, or your statistics. Because you have a coincidence measurement, whenever you add detectors and coincidence, this will greatly decrease your statistics, as it's much more unlikely for a detector you have to have coincidence as opposed to a single detector trigger. This is also dependent upon how far your detectors are separated. So as you separate your detectors further and further away, you can imagine there's less variation. The error associated with where your detector interacts will decrease. As you can see, we have detectors that have some kind of thickness to them, and there's some kind of width to them. So we can have a path length going from a neutron can interact at the very front of the detector, very back of the detector. You can also take a arced length where it doesn't go straight, but it might hit the edge up here. There is going to be some variation in our distance, and this variation will decrease as we increase the spacing of our detectors. This will decrease our uncertainty there. And so now that we have all of these different neutron energies, and we have different light output associated with these, we're able, so long as we're able to get an idea of, we're able to quantify where this edge actually is. You can do a Berks, you can not a Berks, but you can apply a Gaussian, try to fit a Gaussian to this edge, and have consistent edge percentage. So as you're able to do that consistently, you'll have a light output for single energies. And from there, you'll have all these different points you're able to fit your Berks light output function, fit your Berks function to get these values for both A and values B. And notice that we'll get the uncertainty within this distribution will increase as we increase in energy. If we were to look back at this distribution here, our count rate, our counts at very high energies we get very few counts at these high energies. There's going to be greater uncertainty associated with those values. This is a setup of what that time of flight looks like within the lab, where you have our californium source at the far back, californium, and our two different detectors here coupled to a PMT. So this is a still beam detector on the bottom and an organic glass detector on the left. And the reason why we have two of them at the same time is that these are very long experiments. This one, I believe, for this publication took well over 2 weeks. And just because of the statistics on it and how long that flight path is, it just takes so long to get an adequate number of counts, so long as you're not using a very, very strong source. So as a user who's doing these kinds of measurements, you must balance your source strength, your error thresholds, and how long you have to work with, because you don't want to just, it's inconvenient to have a neutron source in your lab for 3 months at a time. So you have to be considerate about these timings. Another thing you have to consider is, of course, room return here. So you can see there's a polyethylene shadow bar here. And so what that does is that in the previous little animations I showed a very idealized system where you have a single neutron that passes through as if there's a vacuum and it's only going one direction. Remember, these are isotropic sources. They'll produce in all different directions. So your neutrons can bounce around at any different point and they might not take a direct flight path. Neutrons can pass, instead of going straight, they can bounce off the floor and we get something called, so we get this different path here. So we can minimize this by a number of ways. For one, we can have it far off the floor and far away from our walls to minimize these number of counts, but we'll always get some kind of some number of neutrons scattering this different way. And we can quantify this effect by putting a polyethylene bar, which will essentially slow down these neutrons that are going straight, and we'll get rid of those counts, and we only see these counts from the scatters. You can see the impact of the shadow bar in this distribution to the right, where we have our bare system, this one here in the circles, as well as the shadow bar, where we have all these scatters. So this is a look at all these neutron counts. So we go from this rounded distribution that includes all these, which is superimposed upon our actual distribution we want for this time of flight. Another component of this is for characterization of these detectors, of course, looking at wavelengths. So within our scintillator, we want to have our emission wavelength and our absorption wavelength to be at different wavelengths so that we don't have as much self-absorption. We want, whenever we have light produced in our scintillator, we want that light to be captured by our photomultiplier tube, or CPM, as opposed to being reabsorbed by a scintillator where we lose that signal. This is done with specialized machines such as a fluorescence spectrometer, which will give us a look at what these emission wavelengths look like. And so the one on the right here is for the primary fluorophore within organic glass detectors, or P2. So we can see that wavelength range will emit in the blue light. So with these kinds of machines, we're also able to verify that the wavelength that our scintillators produce or emit in is well tuned for our different detectors, as different light readout systems will favor different wavelengths of light. Right. From there, I would like to thank the MTV for applying or giving funding for outreach opportunities like this, and I'd be free to take questions.
Excellent job, Ethan. There are a couple of questions in the chat. One of our guests asks, you said that as energies increase, resolution tends to increase due to getting more charged particles. Does this hold for scintillation detection where you're detecting photons? Is this application is the better in this application is the better resolution at high energies just a byproduct of dividing by the higher energy level?
Um, yeah, yes, this is for your photons. So let me go back. So this right here is energy resolution as a function of photon energy. And the idea here is that whenever you have whenever you have a photon pass through your detector, have a certain energy, as has more and more energy, it will create more light in your detector. And when you have greater light output, you have dividing, sorry. Is it in applications, is better resolution at higher energies, a byproduct dividing the by a higher energy level? No, it's for you're producing more information carriers to work off of. For a scintillator, you're producing more photons to be captured, more photons to be read out by your photon multiplier tube or your SciPM.
And the more samples you have, the less the relative error is.
Yes.
Someone also asked, what is the expected value of the figure of merit for a good optimization? Can it be compared to a signal to noise ratio for other types of measurement as a performance indicator?
I wouldn't say it's a analogous to signal to noise ratio because it's hard to because you don't have like a noise idea here. You could better think of it as it's an optimization to make sure that because the separation of your peaks is dependent upon a few things. Let me just pause it here. So this figure of merit is heavily dependent on, of course, your threshold as well as the time slice you do. This tail length. So you can see it's very poorly resolved until around 20 nanoseconds here. In a good value, so another thing I also want to mention is that you have these different figure of merit values at specific energies. And also you might want to think about how you're defining your figure of merit. So you can do a figure of merit calculation where you define it by, I'm going to look at all the pulses past this specific volt integral value, which will correspond to, let's say this corresponds to 50 kV, and that's a threshold, and we're going to take all this data, collapse it onto one axis seen on the left, and do that figure of merit calculation. And that gives you a figure of merit value for one value. Or you can introduce more common where you slice it up to different values, slice it up into specific points, and you get a figure of merit as a function of your energy for this plot. So it's really dependent upon making sure that you have good statistics, your slice width, and you also have your threshold makes sense. As you increase that threshold, you're going to increase that figure of merit. So you have to make sure that whenever you're doing these comparisons between different detectors, like let's say you're trying to compare that to literature, you want to make sure that you're using the same thresholds. You're treating your process of calculating figure merit is the same between your publication and their publication. But I wouldn't say it's a idea of like signal to noise ratio. It's more so you as a user making sure that you're getting the best results out of the data that you have.
Great. How does the digitizer convert the electric current to the desired signal?
Yeah, so whenever we have our digitizer, we have some kind of pulse, our voltage pulse or difference in voltage, um, coming into our detector. And what it does is that it goes from this voltage to a channel number. So within a 14-bit digitizer, we have 2 to the 14th number of channels. So we go from voltage into channels. So it gets an amplitude value for all these, gives us a channel amplitude there. And there's a number of different methods it does this. I believe there's like a clock version of this where you have whenever you, so sorry, there's many different ways that we actually do the process of where it digitizes the pulse. And one is I'm blanking on the specific name of the clock method, but I know they're all listed within NOL itself. We're able to, it just, uh, it will vary by the detectors. I'm not sure which one Kane uses.
Okay. Only by looking at a neutron spectrum with no calibration is it possible to decide which neutron source it is, like fissionable Californium 252 or alpha N source like AMB.
I would say yes. I think it'll be pretty easy to figure out if it is a Californium source based upon the distribution that they have is just fundamentally very different. For California, you have this plot here on the right, as opposed to for instance, like a poopy will have these various peaks associated with that spectrum itself. So you'll see a bit of a difference there. They'll also have so it's yeah, you could based upon their shape itself.
Okay. If anyone has any other questions, please go ahead and submit them. Okay, we're not seeing any other questions. Is there anything else you'd like to talk about, Ethan?
No, I think that covered about everything. All right. In that case, thank you everyone for coming, and we'll see you tomorrow for the final lecture of the summer school.
Oh,
Okay.
I do see a couple more now. How are these detectors useful in the power reactors and high neutron flux environment? Like, can we improve their rigidity?
Rigidity in
I assume he means resistance to radiation damage because we're talking about power reactors and high neutron flux.
I I wouldn't say these partic these particular detectors are too useful for inside reactor monitoring. Um, and there hasn't been a lot of studies on detector like radiation hardness. There's one publication for space applications on organics that compared them for space applications, where they did both gamma and neutron dose, looking at radiation hardness for those. But I'm unaware for ones for specifically for power reactors.
Okay. Then one final question. How do you optimize pulse processing algorithms for accurate characterization of organic scintillators in mixed neutron and gamma ray fields? And what are the key challenges in pulse shape discrimination?
Yeah, so one challenge that is one thing that you do within your whenever doing this kind of processing is that you do cleaning of your data. So here on the right are pulses that are very clean. It's a single pulse, so we have that clean amplitude in our tail. This is not going to be the case with all your data that you get from a system. In some cases, you're just going to get a single noise pulse, and that's all you get. Small pulse, that's it, and you'd have to remove those pulses. In other cases, where if you were to have much higher activity source, or you get too many counts at once, you might experience something we call pulse pileup. Or instead of just having one pulse in a time window, you have a pulse and another pulse on its tail itself. So whenever you're building these pulse processing algorithms, you have to be careful that in addition to optimizing your tail start time and optimizing that, you have to be careful that you're filtering out all these pulses, making all these pulses that have the double pulse in there. Because if you imagine, if you have a second pulse here, that's going to greatly increase your tail amplitude. So you go from having a clean lobe to increasing to getting all these extra. You might get R values greater than one, which is not R values greater than one, significantly higher R values when you shouldn't be having them.
Okay. All right then. If there are no other questions, then let's reconvene for Dr. Selinger's lecture tomorrow. Thank you, Ethan, and thank you everyone for attending.
All right. All right. Thank you.